I'm going to be talking about parallelograms and rectangles. So let's start with definitions. Parallelograms are quadrilaterals with parallel pairs of opposite sides. Okay, a quadrilateral, you may recall, is a polygon with 4 sides. A polygon, you may recall, is a figure in a plane with straight line segment edges. All right, let me draw an example of a parallelogram. All right, and let me draw another example. So you will notice both of those examples have opposite sides that are parallel, both pairs of opposite sides. Okay? Now let's define rectangles. Rectangles are parallelograms with interior right angles. So rectangles are parallelograms, which means they're quadrilaterals and polygons as well. And so they are parallelograms with right angles, so I can draw a couple of examples. Okay? Now, let's use these definitions and other facts that you know about geometry to try to prove some assertions about parallelograms and rectangles, shall we? All right, so I'll write a couple of assertions and you pause the video and see if you can answer one or more of these, okay? Prove that opposite sides of parallelograms are congruent. Prove that opposite angles of parallelograms are congruent. Prove that adjacent angles of parallelograms are supplementary. Prove that diagonals of parallelograms bisect each other. And then let's add a rectangle proof. Prove that diagonals of rectangles are congruent. All right, so pause the video now if you like and answer as many of those, or prove as many of those as you can. Okay, so I will now show you how you can argue each one effectively, how you could make a rock-solid proof based on previously covered material. Okay, so for the first one, let me draw a parallelogram. And I'm allowed to divide any parallelogram into 2 triangles by drawing a diagonal. Okay, and let's keep thinking about what else we know about a parallelogram that has a diagonal, as I've drawn it there. We know that the blue diagonal is a transversal with respect to the pairs of opposite sides. In other words, we have alternate interior angles. Okay, because we know that, again, that we have pairs of parallel sides. All right. Now, notice that the two triangles I've drawn must be congruent because of the ASA theorem. Both triangles share the diagonal as a side, so therefore we know that they have a corresponding sides, a pair of sides that are congruent, as well as two pairs of corresponding angles. Also, remember that congruent triangles have all corresponding angles and all corresponding sides congruent. I often refer to that by the acronym that I pronounce KIPTIC. That stands for congruent parts of congruent triangles are congruent. All right? So that means that opposite sides, now we know they're congruent. And we also know that opposite angles are congruent. All right, so we've used ASA and KIPTIC to show that opposite sides are congruent. And the same line of reasoning can also be used to show that opposite angles are congruent. All right, so using ASA and KIPTIC, I already showed that one pair of opposite angles are congruent in my picture. You can draw the other diagonal and use ASA and KIPTIC again to show that the other pair is congruent. Okay? If that's not clear what I just meant by that, let me make a copy of the original parallelogram, and this time I'm going to draw a different diagonal. I'm going to draw it this way. Right? So we can still use the same points we made in our previous proof. So we have a transversal and parallel lines. So these are congruent. And we have another ASA situation. And so therefore KIPTIC gives us that these opposite sides, these opposite angles are congruent. All right, so that takes care of the first two proofs. Now let's see if we can prove that adjacent angles of parallelograms are supplementary. All right, let me draw another parallelogram because each proof seems to be marking up all the parallelograms that I draw. All right, so I'm going to again draw a diagonal because triangles is using the properties of triangles is a powerful method. All right, now we know that the three triangles of the three angles of a triangle add up to a straight angle. They add up to an angle with a measure of 180 degrees. All right. So if I call this angle 1, 2, and 3, so the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, the sum of those three measures is 180 degrees. Okay? And using the fact that alternate interior angles of two angles formed from a transversal and two parallel lines or line segments, we know that the angle adjacent to angle 3 is also is congruent to angle 1. Okay, so I can put a 1 down there. Now, notice that the angle and also let me write the angle adjacent to the original angle 1 is congruent to angle 3, so let me put a 3 there. Okay, now look at both pairs of adjacent angles that contain angle 2. Okay, they are the measure of the sum of the pairs of adjacent angles that contain angle 2 is the following. Well, it's 2 plus, and then the adjacent angle is composed of combining angle 1 and angle 3. So apparently the sum of supplementary angles is equal to the sum of angle 2, is equal to the measure of the sum of angles 2, 1, and 3. Well, we already know that that's 180, so there you go. We've just proved that adjacent angles of parallelograms are supplementary. Okay? And then to prove that diagonals of parallelograms bisect each other, let me draw another parallelogram if I can fit one on the board. Let's see, how about right here? And all right, so let's first draw two diagonals, and then we'll think about how to show that they bisect each other. And so, again, using we know that we have congruent alternate interior angles. So let me label the congruent angle pairs. Okay, and in the middle we have vertical angles. We know that vertical angles are congruent. So there I've labeled three congruent angle pairs. Okay, now we know that we also know, I'm going to need another bit of information. We know that opposite sides of a parallelogram are congruent. Okay, so I can label the top and bottom horizontal sides congruent. Okay, now we've got a situation where we have two triangles that we can prove are congruent. Okay, the two triangles I'm thinking about are the top one, I'll color it in purple, and the bottom one, I'll color that one in purple. And why do we know that those two triangles are congruent? From ASA. All right, and we know from Kiptich that corresponding parts of those two triangles are congruent. So that means that the angle, like the side, that means that this side has to be adjacent to this side, has to be congruent. That side has to be congruent to the other side I just drew, and then this side that I'm drawing right now has to be congruent to this other corresponding side. Okay, so therefore both diagonals have been, the point of intersection divides each diagonal into congruent pieces. Therefore, we know we've proved that the diagonals of parallelograms bisect each other. All right, now let's do the rectangle one. Okay, so first I will draw a rectangle, and then I will draw diagonals. And for this, I'm going to label the vertices of the rectangle. Let me call them A, B, C, and D. Okay, and because it's a parallelogram, we know that opposite sides are congruent. And because it's a rectangle, we know that we have right angles. Okay, now I'm going to focus on two overlapping right triangles in my drawing. Okay, I'm going to, the two triangles that I'm focusing on are triangles ADC and triangles BCD. Okay? Now, both of those triangles we know are congruent because of the SAS theorem. Okay? And then, because they're congruent, we know that AC equals BD from Kiptich. Okay, so therefore, we know for a fact that the diagonals of rectangles are congruent. All right? Now, let me finish after giving you the formulas for the areas of parallelograms and rectangles. All right? So, you may recall that to measure the area, you have to count the number of a standard-sized square that you can fit in your figure. All right? So if we had a rectangle, and let's say that this rectangle was, let's say that somebody said that it was 3 centimeters by 5 centimeters. Okay? Now, that means that if I take squares with sides of length 1 centimeter, then I can make, I know how many rows and columns of those squares I could make. In fact, I'll go ahead and draw that right now. So I'll be able to make 5 columns and 3 rows of square centimeters. Okay? So therefore, if I made a perfect sketch, then 15 square centimeters would exactly equal the area, would have the area exactly equal to my original rectangle. So therefore the area of a rectangle, this rectangle has an area of 15 square centimeters. For any rectangle, what you do to calculate the area is you multiply the length by the width. Okay? So maybe I can type that out, the general pattern here. The area of a rectangle is the product of its length and width. All right? So if you call the length L and width W, then the area is L times W. All right? Now let's do parallelograms. And let's say that this parallelogram has a height h and the length of the bottom, let's say, is L. The bottom side, that is. So let me represent the height by the letter H, and let me represent the length of the bottom by L. Okay? Notice that that parallelogram has the same exact area as a corresponding rectangle. What is that rectangle? Well, imagine that I chopped a right triangle off of the left side and I moved it to the right side. Okay? So the area of the rectangle is equal to, the area of the parallelogram is equal to the area of the rectangle which I'm shading right now. All right? Furthermore, the long side of that rectangle has a length L. Well, we already know how to calculate the length, the area of a rectangle. That's given already on the board. So therefore, we've just also figured out the area of a parallelogram. I'll go ahead and type that out. The area of a parallelogram is the product of its length and height. All right? If we call the height h and the length L, I can go ahead and write that formula. The area equals the length times the